All right, here we go with the first notes in Unit 5. Unit 5 talks about exponential and logarithmic functions, and today we're going to be talking about exponential functions. So I want to start with this warm up. Consider this table of values here to the left. Let's describe how the value of f of x changes each time 1 is added to x. Or in other words, since this shows plus 1 for x each time, we can just see what's going on with f of x as we move down the rows. So as we add 1 to x, we see that we are adding 3 each time. So to go from 5 to 8, we add 3, 8 to 11, add 3, and so on. So f of x, we add 3 each time. If we were to write an equation for this, we see that we have an additive rate of change. This would be a linear function. We see we can model this using slope-intercept form, y equals mx plus b, where m is the slope, rate of change, plus b, our y-intercept, is our initial value, so 5. So we can model this table of values using the equation f of x equals 3x plus 5. And again, this is a linear function. The graph would look similar to this. Now I want to consider this table of values here. So let's see what's going on as we add 1 to x every single time. So between each row, well, to go from 2 to 6, you could say, yeah, we add 4, but that's not the same relationship between 6 and 18. We want to find a singular rule. So from 2 to 6, instead we can say we're multiplying by 3. And the same is true from 6 to 18, 18 to 54, and so on. So then as we add 1 to x, f of x changes, we multiply by 3 each time. All right, so instead of in example 1, where we have an additive rate of change, we now have, in this table of values, example 2, a multiplicative rate of change. And the type of function that models multiplicative rate of change is an exponential function. The general form for this is f of x equals a times b to the x. So the general form, we've got some number times this base b to the power of x. So our variable is in the exponent. So what does a represent? A represents our initial value. Or in other words, just like how in a linear function our initial value is our y-intercept, it is where x equals 0. So then in this case, what is our initial value? A, x is 0, f of x is 2. So our initial value is going to be 2. B represents our growth or decay factor. So when we talk about exponential functions, we talk about exponential growth or exponential decay. In this case, it is, in every case, it's going to be how the exponential function changes. It's that multiplicative rate of change. In this case, we're multiplying by 3 every time. So our b value is 3. You can put a little side note, how to determine whether or not we're talking about exponential growth or decay. If the b value is between 0 and 1, so you can have this inequality here. If b is between 0 and 1, then we're looking at decay. In other words, the function is decreasing as x increases. If b is greater than 1, however, like in this case here, then we have exponential growth, meaning the function increases as x increases. Let's take a look at examples of exponential functions algebraically, graphically, and numerically. So here we can see that the equation y equals a times b to the x, an example of an exponential function would be like y equals 2 to the x. You could say y equals 2 times 3 to the x, where the initial value is 2, but the growth factor is 3, or the b value is 3. You can write it using parentheses, just like how we can show multiplication using parentheses. You can say 2 times 1.1 to the x. And we're saying that this quantity here, this b value, 1.1, is what's being raised to the power x. In this case, we have b is greater than 1. This would be an example of exponential growth. We can have examples of exponential decay, so y equals 1/2 to the x. So again, this b value is between 0 and 1, so we're looking at exponential decay. And as always, you can multiply as well. So an initial value of 4 with a decay factor 1/2 would look like this. Some non-examples, exponential functions are a distinct function from others. So some non-examples would be any of the other functions that we are familiar with. So an example, a non-example of an exponential function, y equals 2x plus 3. This is a linear function, which has an additive rate of change. Another non-example, y equals the square root of the quantity x plus 1. This is the square root function, again, distinct from the exponential function. And you can also say like y equals 2 times the absolute value of the quantity x minus 3. And we could say plus 1. This is the absolute value function. So as you can see, the exponential function is a distinct function. It's a new function. Graphically, we can see the shape of the exponential function. We've got this L-shaped curve. It's either increasing or decreasing. So some examples, we could see this would be an example of exponential growth, where it's increasing from left to right. An example of exponential decay, it can be decreasing from left to right. So something that looks similar to this. Some non-examples of what an exponential function looks like graphically. Again, a linear function, a straight line is not an exponential function. The square root function, so something like this, is not an exponential function. While it does have that curve shape, this is the square root function. The absolute value function, the v shape, is not an exponential function. And last but not least, a parabola. So that u shape is not an exponential function. And I just want to point out the distinction between a power function and the exponential function. The parabola, or like x squared, would be an example of a power function, whereas these graphs here represent exponential functions. Numerically, we can talk about a table of values. So an example of exponential growth in a table of values, so let's make a table of values, x, f of x. We can say as x increases, 0, 1, 2, 3, exponential growth would show like if our initial value is 2, say we want to multiply by 3 every time. So we'd have the 0.16, 218, 354. Every time we're multiplying by 3. Again, a multiplicative rate of change. We're multiplying by 3. That would be an example of exponential growth. An example of exponential decay, similar, but now we're decreasing. So if our x values are from -2 to 1, we could say values f of x, so -2, 4, 1, 2, 0, 1, and 1, 1/2. Each time this is dividing by 2. So while it's dividing by 2, you can also think of this as a multiplicative rate of change. Dividing by 2 is the same as multiplying by a half. This would have a decay factor of 1/2, a b value of 1/2. A non-example table of values numerically would be any other function. So let's do a linear function. So 0, 1, 2, 3. We'll say our y values or f of x values are, say, 5, 7, 9, 11, increasing by an additive rate of change. This is a non-example of an exponential function. All right, go ahead and flip the page. We're going to try a few more examples. All right, let's take a look at a couple examples. F of x equals 3 to the x and 1/3 to the x. So for number 1, we're going to construct a table of values, x, f of x. And we're going to choose values, we'll say from -2 to 2. So x values, -2, -1, 0, 1, and 2. And let's go ahead and plug that into our equation and see what we get for f of x. So at -2, f of -2, we have 3 to the -2 is the same as 1 over 3 to the +2, or 1/9. 3 to the -1 is 1/3. 3 to the 0, or anything to the 0 power, is 1. 3 to the 1 is 3. And 3 squared is 9. So now we can use this table of values to plot a few points. So at -2, 1/9, you can kind of approximate it's just above the x-axis there. -1, 1/3 would be a little bit higher, probably about a third of the way between 0 and 1. 0, 1, that's our y-intercept. 1, 3, and 2, 9. Now before I sketch in this graph, I just want to have a quick discussion. If we were to continue off in the negative direction, so -3, -4, -5, we would have, um, this would be 1 over 27, 1 over 81 as we continue in the negative direction. And as we continue, we're going to get smaller and smaller numbers, but that will never equal 0. So as we're graphing this, as we move out in the negative direction, we're going to get really close to 0. So as you're sketching this graph, get real close to the axis, but try not to cross the x-axis. We get really close to 0, but don't cross. And it decreases as you move to the left. Okay? This is what we call an asymptote. And I'll talk a little bit more about an asymptote, but let's go ahead and draw that in as a dotted line. So to represent, this is a y value that the function approaches but never actually reaches. So as we move out to the negative direction, we get really close to 0. Because as we move to the negative, in the negative direction, we never actually reach 0, there is no spot where we cross the x-axis. There is no x-intercept. Our y-intercept, I said, it's where it crosses the y-axis, x equals 0. We have 0, comma 1. The domain of this function here, and this is true for all exponential functions, all real numbers. So using interval notation, -infinity to infinity. The range, so the y values that we hit, we go all the way up to positive infinity, and we get really close to 0, but we never reach 0. So our range is going to be from 0 to infinity. And be very careful, we're not including that 0 because we never cross our x-axis. We never hit 0. So this should not be included in your range. All right. So just in summary, this is an example of exponential growth, which increases as x increases. Let's take a look at example 2. So let's go ahead and construct a table of values. So x, f of x, and we'll plug in the same x values. So from -2 to 2. So plug in -2, 1/3 to the -2 is the same as 3 squared, or 9. -1, we're taking the reciprocal, 3. 0, well, anything to the 0 power is 1. Plug in 1, you get 1/3. Plug in 2, you have 1 squared over 3 squared, or 1/9. So again, let's go ahead and plot these points. So we have -2, comma 9. That's all the way up here. -1, 3, 0, 1, 1, 1/3, and 2, 1/9. So before we sketch in this curve, I first want to see what's going on as we move out in the positive x direction. So as x increases, notice what happens to our f of x. We're decreasing 1, 1/3, 1/9, 1/27, 1/81, and so on. We're going to get closer and closer to 0, but we're not actually going to ever reach it, no matter how big x is. So as we're sketching in this curve, make sure that your curve gets really, really close to 0, but try not to cross that x-axis. Do your best to. If you cross, it's okay, but try to not. And then we can draw in our horizontal asymptote as a dotted line at y equals 0. So then our x-intercept, where the graph crosses the x-axis, well, we just said it doesn't cross the x-axis. There is no x-intercept. Our y-intercept, where it crosses the y-axis, is at 0, comma 1. Our domain for all exponential growth and decay is going to be from negative infinity to infinity. All real numbers. You can plug in any value in for x. And our range, what do we get from the function? Well, this is everything from 0 to infinity, not including 0. Okay? So the difference now is this is an example of exponential decay, where this graph, as x increases, the function decreases. So now I want to talk a little bit more about that idea of a horizontal asymptote. So in example 1, as x goes towards negative infinity, or as x gets really, really small, so we're moving in the left direction, the y value, or the function value, approaches or gets really close to 0, but it doesn't ever reach 0. Likewise, in example 2, as x gets really big, so x increases, as x approaches infinity, the y value gets really, really close to 0, but never reaches 0. So we're saying on one of its ends, an exponential function gets closer and closer to a specific y value. This is called a horizontal asymptote. Okay, a horizontal asymptote is a y value that a function approaches but never actually reaches. Um, and we're going to be referencing this throughout the rest of second semester. We're going to be talking about end behavior. This is a concept that it pops up a lot in calculus, so you bet we're going to talk about it in pre-calc. The horizontal asymptote for the graphs above has equation y equals 0. Last thing I want to talk about is exponential growth and decay and also the number e. So take a look at the graph to the right. We have the graphs y equals 2 to the x, so that's this one here. Y equals e to the x, so that's this one in the middle. And y equals 3 to the x, that's this one on the left. So then we're asking, why is the graph of y equals e to the x sandwiched between y equals 2 to the x and y equals 3 to the x? Well, this is because if we consider the value of e, we know the number e has approximate value 2.71828 or so. So 2.72 you could call it. Well, 2.72 is between 2 and 3. So we can say that because e is between 2 and 3, therefore its exponential functions are going to be between 2 and 3, base values, b values, 2 and 3. So then I also want to know, what ordered pair are all of them equal? Well, if you take a look at the graphs, where do they all cross? They all have the same y-intercept, 0, comma 1. So why is that? Well, that's because anything raised to the 0 power is 1. So we can say 2 to the 0 is equal to e to the 0, which is equal to 3 to the 0. All of these function values are equal, and they are all equal to 1. Last but not least, let's go ahead and graph y equals 1/2 to the x. So we're not going to construct a table of values, but start to think about some of those points. At -2, so plug in -2, we have 1/2 to the -2, or 2 squared, is 4. Plug in -1, we have 2 to the 1, or 1/2 to the -1, you could think. Plug in 0, anything raised to the 0 power is 1. Plug in 1, 1/2 to the 1 is just 1/2. Plug in 2, 1/2 squared is 1/4. So we get this shape here. Now notice, what do you notice is similar to the function y equals, or f of x, f1 of x equals 2 to the x? What do you notice is similar? Well, we can see that one of them is exponential growth and the other is exponential decay. But more specifically, so we can write growth versus decay. More specifically, notice that, well, 1/2 is the reciprocal of 2. And looking at these graphs, these are reflected over the y-axis. And we can show that algebraically. We know that 1/2 to the x, well, 1/2 is the reciprocal of 2. So we can say that 2 to the -1 is equal to 1/2. And then we know our power rules. we can multiply our powers, so we have 2 to the negative x. Now, if you remember back at transformations, and this will be a little intro into our next topic, transformations of exponential functions. If you remember back in transformations, when we put a negative in front of our x, this is a reflection over the y-axis. All right, so exponential growth and decay, you can argue, are reflections over the y-axis of one another. All right, so that's a little intro into our next notes, transformations of exponential functions. We're going to get a lot of practice graphing exponential functions, so we'll see you tomorrow in class. Bye.